last section will be about some musical composition that I made and a paper I wrote about that music. Okay, so that's the 4 sections of this talk. Okay, first let's give an introduction to what aperiodic order means. So if you see an A in front of a word like this, it means not, right? So aperiodic means not periodic, right? So you have a structure that is not periodic, but still has a lot of order, okay? Still is very rigid, you know, like a periodic structure. Like if you see a tile in the floor, it's very ordered, it's very structured, but it's also possible to have order and structure for something that is not periodic. So I'm not going to introduce a mathematically precise definition in this talk. The reason I'm not doing that is that there's not really one definition that encompasses everything that people call aperiodic order. Of course, we do mathematics on this, and some things that we do will have mathematically precise definitions, but this concept of aperiodic order really encompasses a lot of things. And I think it's not helpful to give, I don't think there really is a mathematical definition that encompasses everything. But I think this idea is the best way to describe it. When I say aperiodic order, I refer to patterns or structures that are not periodic, but in some way, they are as close to periodic as possible. Okay, so they're not periodic. It's not like a binary sequence. 10101010 is a periodic sequence. So an aperiodically ordered sequence, it's not just 10101010. It's not repeating in that way, but it's still very, very close to periodic, you know, in some way. So I know this is vague, and this is not good to have vague definitions in the math talk, but this really isn't something that has a technical math definition. But yeah, but it does include things that do have strict math definitions. So I'm just going to give maybe the simplest example, the most famous, the most natural example. And this is something called the Fibonacci word. So I'm going to start by defining an alphabet. An alphabet is a set of symbols. So here we have them as 0, 1, okay? But the actual symbols aren't that important. You can call it XY, you can call it AB, you can call it, I don't know, Pikachu and Jigglypuff, right? As long as you have 2 symbols, and we're going to arrange these symbols into words. All right, so I'm going to define a function from A to A star, which is called a substitution rule. And A star, so the fancy math language is that it's a free monoid over A, okay? So A star refers to words with letters from A. Okay, so A is an alphabet, like A, B, C, D, whatever, right? The symbols you use in your alphabet. And A star just refers to words with letters from A. Okay, so for example, 0, 1, right? 0, 1 is a word, right? But so in this substitution rule, the Fibonacci substitution rule takes the input as the letters. So here 0 and 1 are the 2 letters, and outputs a word. So 0, the letter, outputs the word 0, 1, and 1, the letter, outputs the word 0. Okay? Does it make sense? So once again, the numbers really don't matter. As long as you use any 2 symbols, it's fine. You can define it as like SX equals XY and SY equals 0, for example. It doesn't matter. Okay? So a word is just a collection of letters. All right? Any questions about this so far? If not, let's move on. So let's start with initial condition 0. Oops, what's this appearing? Okay, give me a second. This should be here. This is for later. All right, I'm not sure why that appeared. All right. So we start with an initial symbol 0, and we keep applying this substitution rule S. Okay? So we start with 0. That's our initial symbol. And then we apply S. So S takes the symbol 0 and outputs the word 0, 1. Okay? That's what the substitution rule does. And now we're going to apply S again to the two letters in the word, right? So we have 0 and a 1. The 0 will go to 0, 1, and the 1 will go to 0. Okay? So when this happens, we get 0 to 0, 1, and then we apply the substitution rule, 0 to get 0, 1, and then we apply the substitution rule to the 1 and get 0. Okay, so when you apply this S to the whole word, you get 0, 1, 0. Does that make sense? Okay, this step is, yeah, I think it's not that difficult, but if you don't understand it, you should let me know so I can explain it again, because this is kind of critical for the talk. Any questions about this? Okay, just to make sure you understand, can someone tell me what will the next step be? When we apply S to this word 0, 1, 0, what do we get next? Can someone tell me?
I think it's 0, 1, 0, 0, 1.
Very good. Yes, excellent. So we apply S to 0, we get 0, 1. We apply S to 1, we get 0. We apply S to 0, we get 0, 1 again. And indeed, we get 0, 1, 0, 0, 1. Okay, and we can apply it one more, we get this. So a few things to notice about this substitution, right? This process of substitution. Notice that the first few symbols always stay the same, right? So we start with 0, and notice that every step after that always starts with 0. And here we have a 1, right? And every step after that, we'll have a 1. And the third number is 0, and every step after that, we'll have a 0. Okay, and we can continue again and again, this process. And this is what I mean by this. The initial symbols stabilize. Okay, so they stabilize. So when you apply this process again and again, the first few symbols is always the same for every step of this process. The initial symbols are always the same, right? So every step after this, you'll start with 0, 1, 0, 0, 1, 0, 1. Okay, and then we can take this process to infinity, and we obtain this infinite aperiodic word. It's not periodic, right? 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, blah, 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 blah. Okay. So maybe an exercise for you. Okay, if at some point you get bored of this talk, you can try to figure out how do we prove that this is not periodic. Okay, I think that's an interesting thing to try if you can think about that. Okay, but anyway, this is aperiodic. It will not be repeating. Yeah, but this is called the Fibonacci word. Okay, so all of you understand how we obtain this Fibonacci word? So did I explain it? Okay, I did explain why we call this the Fibonacci word, fortunately. Okay, so let me explain why we call this the Fibonacci word, because it's not that important for the talk today, but I think it's interesting. So what's a Fibonacci number? Well, a Fibonacci number is just a sequence where the current number in the sequence is the sum of the two previous numbers, right? So you have 1, 1, 2, 3, 5. Like 2 is 1 plus 1, 3 is 1 plus 2, 5 is 2 plus 3. So every number in the sequence is the sum of the two previous sequence. And we can see here, why do we call this the Fibonacci word? Well, you look at all these strings, right? All these words, all these strings, 0, 1, 0, 0, 1, is a result of combining the two previous ones, right? So if you get 0, 1, 0, 0, 1, you combine 0, 1, 0 with 0, 1. Notice that? I guess the technical term is you concatenate, right? So the 0, 1, 0, 0, 1 string is obtained by concatenating the 0, 1, 0 string with the 0, 1 string. That's where you get 0, 1, 0, 0, 1. And the 0, 1, 0, 0, 1, 0, 1, 0 string is obtained by concatenating the two previous strings. So you see here, you get the 0, 1, 0, 0, 1, and you concatenate with the 0, 1, 0. Okay? So that's why it's known as the Fibonacci word, because you have that similar structure to the Fibonacci sequence. Okay, so we get this infinite aperiodic word. So let's talk about what I mean. So remember, for aperiodically ordered, let me go back to the previous slide. For an aperiodically ordered structure, pattern, we need something that's not periodic, and this isn't periodic. You can sort of see that it's not, right? But you can also try to prove it. I think it's a fun exercise for you. But we want also that it will be as close to periodic as possible in some way. Okay, and let's talk about why do we say that this sequence is as close to a periodic sequence as possible. So a periodic sequence would be something like 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. Now, let's talk about it. Let's try to explain why. And to do that, we have to introduce something called a complexity function. So given an infinite binary sequence W, a word, I guess, we define sigma n W as the number of distinct subsequences of W of length n. Okay, so sigma n W is called the complexity function of order n, and it just counts how many different subsequences does your word have that have length exactly n. All right, let's look at the W to be the Fibonacci word from the previous slide, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, and so on, yeah. So first, sigma 1W is 2, okay? There are 2 subsequences of length 1, and they are 0 and 1, okay? There's just 2 letters in the alphabet. So obviously, there are only 2 possible subsequences of the sequence that have length 1. And there are 3 subsequences of length 2, right? You have 0, 1, you have 1, 0, and you have 0, 0. So notice that we never have 1, 1. There is nowhere in the sequence where 1, 1 appears. Do you see that? 1, 1 never appears in the sequence. So there are only 3 different subsequences, 3 distinct subsequences of length 2. And again, I guess I'm going to assign a lot of homework for this talk. You can try to prove for yourself why doesn't 1, 1 ever appear in this Fibonacci word. Again, that's a very easy proof. It's not very hard to prove that. But because 1, 1 never appears, the complexity function of order 2 for the Fibonacci word is 3, because you have 3 different possible subsequences, and the 4th one, 1, 1, is not possible. Okay, can someone tell me? Okay, don't have to prove it, but just look at the Fibonacci word. What is the complexity function of order 3? So don't try to prove it. Just look at the Fibonacci word and make a guess. What do you think is the complexity function of order 3? So you're counting how many distinct subsequences of this word that have length 3. Yeah, so don't try to prove it. I guess it's not that hard to prove, but I think just look at this word and try to count, just to make sure you understand what this complexity function means. Yeah. So how many subsequences of length 3 does this?
I found 5.
5. What are the 5?
0, 0, 1,
0, 0,
1,
0, 1, 0,
1, 0, 0,
1, 0, 0,
1, 0, 1.
1, 0, 1.
Wait.
Yeah, that's all 4. Yeah, there are only 4.
Wait,
Yeah,
what?
there are only 4. Yeah, there are only 4. Yeah. Yeah, you did find all 4. Very good.
Yep.
Yeah, thank you. Yeah, but anyways, there are a lot of different symbols to keep track of, right? And it gets harder and harder to count, obviously, as the n gets larger. But yes, in general, yeah, it's 4. For n equals 3, you have 4 different subsequences of length 3. And in general, for n, right, the number of subsequences of length n is n plus 1. So again, this is not very hard to prove. Yeah, but that's what it is, okay? Sn of w is n plus 1. So there are always n plus 1 distinct subsequences of length n, okay? Right. And so why do we say, so again, what does this complexity function have to do with anything? So let's imagine a periodic sequence. Yeah. If your P is a periodic, if you have P, which is a periodic binary sequence, you can check that Sn of P must be a bounded function, right? That eventually, even if the n increases, the SNP doesn't increase. Let's look at a simple example. Let's say 0, 1, 0, 1, 0, 1, 0, 1. Yeah, 0, 1, 0, 1, 0, 1, 0, 1. If we try to calculate the complexity function, there are two words, subsequences of length 1, two subwords of length 1, right? 0 and 1. If you have 0, 1, 0, 1, 0, 1, there are two subsequences of length 2, right? So if you look at the sequence 0, 1, 0, 1, 0, 1, 0, 1, you have two strings of length 2, two subwords of length 2, rather. And in general, you notice that if your sequence is just 0, 1, 0, 1, 0, 1, 0, 1, for all n, right, you just get Sn of P to be equal to 2. Notice that? So it will be a bounded function of n. As n increases, eventually the complexity functions will stop increasing. Okay, you can check that yourself for any binary and for any periodic sequence. So the simple one is 0, 1, 0, 1, 0, 1, 0, 1. But even a more complex repeating pattern, the SNP will end up to be bounded. Okay, so for a periodic sequence, the complexity function is low, it's small, it's bounded. And there's a theorem for those people who study these sequences called the Morse-Hedlund theorem. And this proof is actually quite difficult. Yeah, I'm not going to prove it. It's actually quite difficult. But it says that for any sequence, binary sequence that is not periodic, aperiodic, the complexity function of order n must be bigger or equal to n plus 1. Okay, so for periodic, it's always bounded. But for aperiodic, it must be bigger or equal to n plus 1. So in some sense, we can say that if the complexity functions are small, this means that the sequence is close to periodic, right? Because periodic is bounded, okay? So all aperiodic sequences are unbounded, but if the complexity functions grow slowly, in some sense, we can say that they are close to periodic, right? Because for periodic functions, they're bounded. For aperiodic functions, they go to infinity. This must go to infinity. But you see that this Fibonacci word goes to infinity as slow as possible, right? So the complexity function must be bigger or equal to n plus 1. And for the Fibonacci word, it's equal to n plus 1. So this sequence of complexity functions grows as slowly as possible. And for that reason, we can say that this Fibonacci word, it's not periodic, right? But it is as close to periodic as possible, right? You cannot have a sequence whose complexity function grows more slowly than this one. So either it's bounded, in which case you are a periodic sequence, or it's unbounded, right? Every aperiodic sequence will have an unbounded complexity sequence of complexity functions. In that case, it must be bigger or equal to n plus 1. And the Fibonacci word has the slowest possible growth. So it's as close as possible to periodic. Okay? Yeah, so this is a sense which you say that this Fibonacci word is as close to periodic as possible. All right. Yeah, so this is the aperiodic sequence that has the smallest possible complexity functions, right? You cannot get smaller than that. So that's why we say it's as close to periodic as possible. So this was an example, a discrete example, right? You have a discrete sequence, 0, 1, 0, 1, and so on. Let's go through a continuous example, right? Again, a concept connected to aperiodic order. Let's consider something called a quasi-periodic function. So there are a few different ways you can define it. I'll just do a simple way. So it's just you obtain a quasi-periodic function by adding two periodic functions whose periods are what we call not rationally dependent. Okay, so we can add two functions whose periods are irrational multiples of each other. So cosine 2 pi x has period 1, and cosine of x has period 2 pi. And of course, 2 pi and 1 are not rationally dependent. So 2 pi is an irrational multiple of 1. Okay, so the two periods are irrational multiples of each other, 2 pi and 1. So first, let's verify. Remember, aperiodic order has two things. First, we say that it's not a periodic pattern. So we want this function to not be periodic. And we also want it to be as close to periodic as possible. So first, how do we know that this function is not periodic? Of course, both the parts are periodic, right? Cosine 2 pi x is periodic. Cosine of x is periodic. But when we add them together, it will not be periodic. So how can we see this? So let's check. We plug in 0. What do we get? Of course, cosine of 0 is 1, and cosine of 0 is 1. 1 plus 1 is equal to 2. So when we plug in 0 to this function, we get 2. But notice there is no other x for which fx equals 2. Okay? Does it make sense? So this function reaches the value 2 exactly once. Right? And that's not possible because a periodic function will reach every value an infinite number of times. Can we make sure that the audience is muted? I'm hearing some like microphone sounds. Yeah, anyway. But anyway, do you understand why this function cannot reach the value 2 other than at x equals 0? Do you see why? Yeah, can someone answer that? Why does this function only reach the value 2 at x equals 0? So think about, sorry, someone wants to answer?
The maximum of each function is 1, then you add up at most they can get to 1, right? I could get to 2.
Yes, at most 2, yeah, right. But why does it only reach 2 at one point? Okay, but that's a good start, right? So both of these functions, the maximum is 1. When does cosine x equal to 1? And when does cosine 2 pi x equal to 1?
At 2 pi.
Right, very good. So cosine x equals to 1 at 2 pi, 4 pi, 6 pi, 8 pi, and so on. When does cosine 2 pi x equal to 1?
When x is multiple of 2.
X multiple of x is an integer, right?
Yeah,
Any integer. Yeah. So you see that the left part only becomes 1 when x is an integer, and the right part only becomes 1 when x is a multiple of 2 pi.
Yes.
And there is only one integer that is also a multiple of 2 pi, and that is 0.
Yeah.
Right? Yeah, so that's why this function only reaches 2 once. But that means it cannot be periodic, right? Because a periodic function will reach every value an infinite number of times. But if you look at the graph, right, this function looks like it's periodic, right? It looks very much like a periodic function. If you draw the graph, you can go to Wolfram alpha or whatever, right? This function looks very, very close to a periodic function. It looks periodic to the naked eye, right? If you're not looking very closely, it does look periodic. And in fact, there are values of x where fx gets closer and closer and closer to 2, even though it never reaches 2. Does it make sense? Because obviously, there are no integers that are multiples of 2 pi. Right? There's no integer other than 0 that's a multiple of 2 pi. But you can have integers that become very, very close to a multiple of 2 pi. For example, we know that pi is equal to 22 over 7, right? So 2 pi is 44 over 7, right? So 2 pi is close to 44 over 7. But that means that 7 times 2 pi is very close to 44. Does it make sense? So 44 is very, very close to being a multiple of 2 pi because 7 times 2 pi is very close to 44. So this function gets very, very, very close as you want it to, infinitely many times. So if you look at the graph and you're not looking very carefully, you see that it's periodic, even though it's not. So again, this is a function where it's not periodic, but it's very, very, very close to periodic. In fact, as close to periodic as possible. And you obtain this by adding a function adding two periodic functions, but their periods are irrational multiples of each other, you always get a pattern like this. Okay, that's another example of an aperiodically ordered structure, and this one is continuous. Okay, any questions about this function? Yeah, it's a very interesting function. You should try to play around with it. Look at the graph. Yeah, it's super interesting. Okay, let's move on. Why do we care about these aperiodically ordered structures? Structures that are not periodic, but close to periodic as possible. Because they appear in nature. So there's a material called a quasi-crystal. So a quasi-crystal is, it's like a crystal, but not really, okay? They can be found in nature, but you can also build them in a lab. I think you can make them in the lab by you take a crystal and then you heat it up very fast and you cool it down really quickly. Okay, so a crystal structure is periodic, but a quasi-crystal is not periodic. Okay, and this is a diffraction pattern of a quasi-crystal. When you shine a light, like a laser, on a quasi-crystal, you get a pattern that looks like this. Okay, so this is not a periodic pattern, but it is very, very close to periodic, and it's an example of an aperiodically ordered pattern. And this pattern actually won the 2011 Nobel Prize in Chemistry. So the guy who discovered it, Dan Xiamen, won the Nobel Prize for discovering this material called a quasi-crystal. Okay? Yeah, so, and their structure, their atomic structure, has aperiodic order. So that's why when you shine a light, you get an aperiodically ordered diffraction pattern. Yeah, and that's why after this discovery, people started becoming more interested in studying these aperiodically ordered patterns because they are a good model to understand this material, the quasi-crystal. So because of the applications to material science, people started becoming interested in looking at aperiodic order. And this is a famous example of Penrose tiling. Okay, I'll put it next to the the Penrose tiling is an example of an aperiodically ordered geometric pattern, and compare with this quasi-crystal, right? So the quasi-crystal, you can see that it has 5-fold rotation, right? And this is actually how we know that it's not periodic, because the only way that you can tile a plane with a regular shape, a regular pentagon, is with a triangle, a square, or a hexagon, right? Those are the only 3 ways you can tile a plane with a regular pentagon. But this diffraction pattern, you can see that the rotation angle, the rotation symmetry, is 72 degrees, right? So you can see that's a 10-sided shape here, right? These are all 10-sided shapes. So they're pentagons, or I guess decagons, right? So you cannot have a periodic pattern tiling the plane with a 72-degree angle. So you see there's 72-degree angles here everywhere, right? So the best you can do is with something like this, which has also a 5-fold symmetry, a 72-degree rotation symmetry. So yeah, the Penrose tiling is in some way a model for this quasi-crystal structure. But we'll talk about this Penrose tiling a bit later. Okay. And aperiodic order, because of this, actually a big part because of that discovery, aperiodic order has become a key concept in mathematical physics and spectral theory. So a recent Fields Medal, Arthur Avila was a Brazilian mathematician who won the Fields Medal, I think, last one, like the previous Fields Medal, because of his research on the dynamical systems that have this aperiodic pattern. So the dynamical systems are not periodic, but they are close to periodic as possible, right? And the dynamical systems that he studied were connected to the Schrödinger operator and quantum mechanics. Yeah, but this research that's connected to aperiodic order was a part of his the reason why he won that Fields Medal. Yeah. So why are they interesting mathematically? So we know there's a connection with material science, but there's also a very interesting mathematical reason why these aperiodically ordered systems are interesting. It's because aperiodic order is like in between a system that's periodic, right? So periodic systems are very, very ordered and random. So random systems are not ordered, right? They're random. So sometimes you have, you know that the system behaves this way if it's periodic, and you know that a system behaves another way if it's random. And these aperiodically ordered systems can sort of be the transition in between. Okay. Let me maybe go through a quick example. So again, this isn't very okay. I'm going to go speed up a bit here since I'm a bit behind time. But let me very quickly go through. So some of you recognize this operator. This matrix is called a Schrödinger operator. Okay. It's from L2 of the positive integers to L2 positive integers, and it's a matrix, 0 here, 0 here, 0 everywhere else except for the middle three diagonals, and there's 1 on the off diagonal, and the middle is called the potential sequence, V0, V1, V2, V3. Okay, this is called the potential sequence, and you have an eigenvalue equation called the discrete Schrödinger equation. So the Schrödinger equation is the most important equation in quantum mechanics. It tells you how particles move, right, in your environment. And it can be expressed, there are a few different forms of the Schrödinger equation, but one way you can express it is as an eigenvalue equation for this matrix, HC equals EC, okay? So of course, when you have an eigenvalue equation, you care about the spectrum, okay? Okay, so some of you might not know spectral theory. If you don't know spectral theory, I'll just try to explain very briefly. So in your linear algebra class, you know that the spectrum is the set of eigenvalues, right? All the eigenvalues, the set of eigenvalues is called the spectrum of the matrix. And every matrix will have a spectrum that consists of finitely many points, okay? But this is not a finite matrix. You see this matrix? It goes on forever, right? This matrix is a matrix of infinite length and infinite height. So the eigenvalues, so the spectrum doesn't just consist of finitely many points. The spectrum can be any set on the real line, okay? So the spectrum is defined this way, okay? If you don't understand this, that's fine. It's not really important for the talk. But just know that this is a generalization of what you learn about the spectrum in linear algebra, which is the set of eigenvalues. Okay, but for an infinite matrix, the spectrum doesn't have to be a finite set of points. It can be any subset of the real line. Right? It can be any subset of the real line. Okay, so if your Vn, if this sequence of potential, the potential energy sequence, if this is periodic, your spectrum is in fact a union of closed intervals. Okay? If your Vn is random, if you just randomly choose the Vn, like an independent, identically distributed random variable, then almost surely, because it's random, we can't say 100% sure, right? Okay, we can say 100% sure, but it's not always the case, but almost surely, it will be a countable union of discrete points, eigenvalues. You have eigenvalues, but not finitely many, okay? So you see that there are two different behaviors, okay? If it's periodic, you get closed intervals. If it's random, you get points. So what happens when we have Vn be a Fibonacci sequence, an aperiodically ordered sequence? We end up something between closed intervals and points and discrete points. Okay. So what is a set that's between closed interval and discrete points? A fractal, right? For example, the Cantor set. A fractal set we can think of it as something between point sets and intervals, right? And in fact, if your Vn is, for example, a Fibonacci sequence, like we studied earlier, your spectrum can be a fractal. Okay, so yeah, so you can see a really weird behavior. So this is really weird. This is not normal, right? This is a very interesting thing because normally a spectrum is a very well-behaved set, but here we can get a fractal instead. So that's pretty interesting. Okay, one reason why this aperiodically ordered things are important in quantum mechanics because you get very unusual spectrum when you apply it to the Schrödinger operator. So okay, but what does it mean? What does it mean that the spectrum is a fractal? Okay, but let me maybe give a bit more of a physical interpretation. So we talk about quantum walks very briefly. So you know what a random walk is, right? A random walk, for example, is Brownian motion. You know that air moves according to Brownian motion. It moves randomly, right? So how does the motion of so a lot of objects have that movement, like the movement of air, right? It's random, so we call it's like a random walk. Quantum walk is like a quantum mechanics analog of a random walk. So I'm not going to explain that very much, but that's just it. It's like Brownian motion, but Brownian motion is of course a classical physics concept. Quantum walk is like a quantum version of that Brownian motion. That's one way to think about it. And we want to know, okay, what's the behavior of that quantum particle that's randomly moving around if you have different environments, okay? And it turns out that if your environment is periodic, you have a periodic environment, like the potential is periodic, then your particle has what is called ballistic transport. So it goes to infinity very, very fast, okay? So it starts moving around randomly, but it always ends up going to infinity very, very quickly. If your quantum walk is in a random environment, your environment is just random, there are random potentials everywhere, then there's a concept called Anderson localization. It stays localized, okay? Which means that it stays in one area, it doesn't go off to infinity. Okay? It just stays where it is. So this is something that was one of my papers, okay, in JMPA, journal something, it's a French name, Journal Mathématique Aperiodic Appliqué. It's a French journal, right? But you can just search demonic Xiamen Ong, you can find it. And we prove that if you have a quantum walk, okay, which is a quantum version of Brownian motion, a random walk, and you have an environment that is aperiodically ordered, then you can exhibit something called anomalous transport. That is, the particle goes to infinity, but at a sub-ballistic rate, like very, very slowly, okay? And this is something that's unusual because normally particles in this system, either they stay where they are or they go to infinity quickly. This, to our knowledge, this was the first example of a quantum walk that has this behavior where it goes to infinity but slowly, right? In fact, for classical Brownian motion, that also doesn't happen. For random walks, for like the Brownian motion, you either have localized behavior, the particle stays where it is, or it goes to infinity, okay, depending on the environment. You don't have this phenomenon where it goes to infinity slowly. But this is, to my knowledge, the first and maybe the only example of a quantum walk that has this behavior. And you got that because aperiodically ordered patterns are between periodic and random, right? So random, this stays where it is. Periodic goes to infinity quickly. So in between that, when you have aperiodic order, it goes to infinity slowly. This was a new behavior, right? That had not been observed before. Okay, so that's one reason why this aperiodic order is interesting in my math research. Okay, I knew you're here for a math and art and music talk, so let's talk about art and music now. So let's skip the physics. Let's talk about art. And first, I want to mention this artist called MC Escher. And he's known for incorporating mathematical ideas in his art. So here's a famous self-portrait. This is what Escher looks like. He drew himself like this. And you see that he's very interested in geometry. And you can see they have this spherical mirror. And he's trying to analyze how does a spherical object reflect light. So that's why he drew a self-portrait in that way. Okay, but he's a person, he's an artist. Even though he had no mathematical training, he really loves mathematics. And almost all his art involves mathematics in some way. Okay, this is one example of it. But I'm interested in one particular type of art he does, his tessellation or his tiling art. He's very interested in periodic patterns that cover the plane. Okay, so here's an example. You see a bat, a bird, and an insect here. And he sort of arranged the patterns together periodically to cover the plane. Okay, here's another example. You see a fish and a frog here. You can see how he joins the patterns together in a periodic way to cover the plane. Okay. Here's another example. We have the same shape, right? The two shapes. They're just a horse, but different color, and they also cover the plane. So my thought was that Escher only worked with periodic patterns, repeating patterns. So I wanted to work with a Penrose tiling, all right? Something that's non-repeating, okay? Oops. Okay, so this is a Penrose tiling. It's an example of a non-repeating pattern. It's aperiodically ordered. It's not repeating, but in some way it's close to repeating as possible. And this actually has been used in art before. Even before, it was discovered in the 70s, but in fact, it appeared in art very early on, like maybe even the 15th century. Okay, it appears a lot in Islamic art. This is the Darb-e-Imam shrine in Isfahan in Iran. Okay, and you see these patterns here. These are Penrose tiling patterns. So even though the Penrose tiling is named after Roger Penrose and was discovered in the 70s, the pattern actually appears in Islamic art from like the 1500s. Okay, so yeah, because it's not, even though it was discovered in the 70s because of the quasi-crystal, right? That's why people are interested in these patterns. But it actually appeared in art earlier, but nobody noticed it. Okay, it appeared in like the 15th century. Okay, so let me explain a bit of what the Penrose tiling is. I'll do this very quickly. Give me a second. Yeah, I should have prepared this earlier, sorry. Give me a second. Penrose tiling. Okay, so Wikipedia has a very nice animation of Penrose tiling. So there are two different types. I'm going to focus on this kite and dart tiling. Okay, let's look at this picture. Okay, so you start with this kite tile, right? And then you can have a system, a rule. Give me a second. You have a rule where you, yeah, sorry, I thought the rule was here. Give me a second. Tiling's encyclopedia. Okay, so this is a really cool website. You can look at this tiling, but yeah, sorry, I should have prepared this a bit earlier, but I forgot about it. Penrose tiling. No, I want kite and dart. Give me a second. Penrose kite and dart. There you are. Okay. So you see how, so remember, it's similar to the Fibonacci sequence where you had 0 goes to 0, 1, and 1 goes to 0. So instead, we have this is like a 2D version of the Fibonacci word. You have this dart tile, it gets transformed to this, and this kite tile, it gets transformed to this. So a dart tile gets transformed to 2 darts and a kite tile gets transformed to 2 kites and 2 darts. And when you apply this transformation with any initial condition, you apply it over and over again, you get this full Penrose tiling. Okay, let me look at it. Yes, here you go. See, you apply that transformation over and over and over again, and you end up with this thing called the Penrose tiling. Okay, so let me show you. My program. Maybe you can show this a bit more clearly. Right, let's run the program. So let's start. Right, we start with a single kite tile. Okay, and then we apply it one time. Wait, where's my thing? Give me a second, I can't find my, there you are, okay. Let's apply this process one time, okay? So the kite tile transforms to 2 kites and a dart, 2 darts, okay? And you can see this from this website, okay? You can see that a kite tile becomes 2 kites and 2 darts, okay? And then we apply again. We apply again. Okay, and then we apply again, repeating this process over and over again. And when we do that, we end up with an infinite pattern, right, with these kites and darts. Okay, let's go to a bit more now. Let's do 8 maybe. So when we repeat this process over and over again, we get this Penrose tiling. Yeah, okay. Does it make sense? So that's how, maybe let me zoom in a bit more. Let me zoom in. That's a bit too small, I think. When you apply that process over and over again, you get this Penrose tiling. Okay, so that's where this comes from, all right? And now I want to apply Escher style art to this. Okay, so if I go to my program, let me see, where is it? This workspace, Penrose kite dart. So let me go to my program. Not here, bin, I think, yes. Okay, so you see that I have my dot, and I have my kite here. Okay, so let me delete this, delete the kite, delete the dot. Okay, and let's look at, I can replace that with another pattern. And the pattern I want is this fisherman drawn. Okay, this one, right? So I have this pattern instead. So I replace the dot with something like this. This is a fisherman. Okay, let me replace that. So copy, oops, let me replace that. So copy, oops, sorry, I shouldn't have closed that. Dropbox, Quick Workspace, Penrose Kite Dart, bin. Okay, so let's copy that, paste, call this dot, and I have a turtle. Okay, my turtle shape. And I call this kite. Okay. And when I do that and I apply my program again, oh, let me, it's a bit not good. Let me zoom in a bit more. Okay, so I apply these two shapes. I need to zoom in a lot more. Not good. Okay. Sorry. I think that was a bit too big. Give me a second. Let's not do 8. Let's do 4. Let's do 4, I think. Whoops. Okay. Yeah. I'm not sure what the correct parameters are. Let's try this instead. Okay. Good enough. All right. So you have this, and you see that the turtle is my tortoise, and my fisherman are arranged according to the kite and dart Penrose tiling, similar to what Escher did. So I had to modify the shape a little bit, make it look nice, and I get a kite and dart shape like this. Okay, let me show you the full picture. Show you the full picture. So at the end, I get something like this. Where is it? Dropbox, art, and I got fisherman and turtle. No, there you go. All right. So finally, I get this. Okay, after I drew the pattern and I colored it, I get this pattern of a fisherman and a turtle, according to Penrose tiling that way in the style of Escher. Yeah, and if you're interested, you can see more of these. You can see more of these art in my website, drong.my/art. And you can see some of the other art I've done in the same way, right? Where I've used the Penrose tiling, modified the shapes, and created these art patterns that look like this. Okay, yeah. And I think it's a really cool visual object. So again, I'm not using exactly the same Penrose tiling. I'm modifying it a little bit by making sure that they still fit. And you get some really interesting patterns that way. Okay, so that's it for the art part. Okay, now let's talk a bit about music. Music that conveys infinity. And this is another application of aperiodic order to the arts. To introduce, this was inspired by something by Xiamen. Right, Xiamen is a French composer, and he wrote this piece called Quartet for the End of Time. This is the French title, Quartet pour la fin du temps, something like that. And the first movement is called the Liturgie de Cristal. So this is from a book analyzing this music. So what is Liturgie de Cristal? So it's a quartet, so there are 4 instruments. The piano part has a cycle of 29 chords and 17 durations. So when you want to repeat again, 29 times 17, right? I'm not sure how much this is, but it's about 400, I guess. Yeah, about 400, all right? So we have about 400-ish. So we have 29 chords and 17 durations. And if you want to repeat again, so this repeat, the 29 repeats and 17 repeats, but for both to repeat at the same time, you need about 400 cycles to return to the same starting point. And that's just the piano, right? You also have the cello, and they have 5 pitches and 15 durations, okay? So to repeat the starting point, you would have to, I guess 15, right? So to repeat everything, you have the piano part, which is 17 times 29, and then the cello part, which is 75, I guess, 5 and 50, yeah, all right? So when you want to repeat, so technically you have this repeating patterns, but they all have different periods, and to repeat to the starting point would take about 4 hours, okay? And Messiaen only shows a small part of that, but because it seems like when you have these repeating periods that have different periods, right, that are relatively prime, it seems like the music becomes very, very long because it takes a very, very long time for the music to come back to where it started. Okay, so I'm going to ask to share this music. Okay, who's the presenter? Okay, so can someone please share that YouTube piece? Noazizal, can you share the YouTube link, please? So I'm going to show you this liturgy, the end of time, right? It's a quite interesting piece. We'll just play a bit of it so you can see what it's like. And you can start with the 10-second mark. The first 10 seconds are advertisement. Yeah, don't forget, you have to enable sound sharing. This is not it. This is just an ad in the beginning. It starts about like the 15-second mark. See, it's a quartet, so there are 4 parts. It's a flute playing, right? So what's happening here is that the 4 parts are just playing a repeating tune. It's just repeating over and over again. But the repetition all have different periods. Right? So the repetition have different periods, like 29, 17, 15, whatever, right? Okay. So it takes a long time for it to go back to the beginning again. So technically, if you were to play this music until it repeats again, it would be like 4 hours, 40 minutes. Yeah. So even though all 4 parts are very simple, they're repeating at different periods. So the resulting becomes very complex. Yeah. Okay, and noise is out. I think that's enough, right? So this is the Liturgie de Cristal, a very interesting piece of music. But that's actually inspired by that, right? Because Liturgie de Cristal, it's made to seem like it's infinite, right? It goes to infinity because the periods are repeating, but at right, it seems like it's infinity. It's meant to sound like infinity, but it's not really infinite, right? It just would repeat every 4 hours and 40 minutes. So it is not really an infinite piece of music because it does repeat. Even though it takes a very, very long time, it does repeat after 4 hours and 40 minutes. And I was thinking, right, could we compose a piece of music like this that is actually infinite? Okay, so Liturgie de Cristal use relatively prime lengths. What if I used irrationally independent period lengths? So remember this function, right? We discussed before. This is an aperiodically ordered function. 2 functions that have a period that's 1 and 2 pi, that are irrational multiples, right? So I decided to compose a simple piece of music, just 2 parts. But the 2 parts repeat, but the repetition is irrational multiples, right? So this is 240 beats per minute, right? And this is 360 over the golden ratio. So remember, the golden ratio is an irrational number. So this part will repeat. We repeat every 60 seconds. No, every what? It's for, yeah. So this part will repeat every second, right? And this one will repeat like I'm not sure how many seconds, but an irrational number. So I have two parts, right? And that like that. And I have a very simple music. And because these two repetitions are irrational multiples of each other, this music actually does go to infinity. It never repeats. You can play it forever, and it will never repeat. Okay. From Narizal, can you share my SoundCloud link? Yeah. So I've also given. So this is the music I composed. I called it Raindrops in A minor. Hopefully, yeah. So there's a SoundCloud link that. Thank you, Nazizal. Appreciate it. Right. So that's an example. Right. Okay. Of course, I just gave you a 30-second clip. But if you were to play the music as I've written it, it will actually last forever. It will never repeat because the two parts are irrational multiples of each other. Am I sharing? Yes. Okay. Okay. Because these two parts, they're repeating, but the repetition, the period length is an irrational multiple. Okay. Okay. That's the end of the presentation. Now I should thank the Malaysian Ministry of Higher Education for this grant funded this research partially. Oops. And yeah, if you want to see the paper so I wrote a paper about this music, and the paper is open access. You can find the link here on my website, www.drong.my. If you want to see my art, is also on this website, drong.my/art. Right. So both the music was a published paper. The art is not, right? But you can see both in my website, drong.my. Okay. That's it for my talk. Thank you so much for USM for inviting me to speak. It was a lot of fun, and I always enjoy visiting the USM math department. Like, you guys are very strong department, very good. I always enjoy going to Penang. And sorry I couldn't come this time. And hopefully there'll be a chance to go back to Penang at some point.
All right, thank you, Dr. Ong. Yeah, it's a very interesting and nice talk. Yeah. So yeah, like you see, all the music, everything. Yeah. Okay, so now we open questions maybe to the floor. Does anybody have any questions that you want to ask Dr. Ong regarding his work or the music or whatever?
Hi, Dr. Ong.
Hello.
Can you hear me? Hi,
yes.
my name is Johnny. Thanks for the talk. It's very interesting. I actually have two questions. I think they are related. So the first question is that, do you know that if there's any relation between the Penrose tiling with the Penrose tribar?
The Penrose
tribar?
Yeah. I've never heard of that. What is that?
It's basically an impossible figure.
Oh, the tribar. Yeah, the triangle bar.
The
yes.
tribar. Yeah. So, yeah, I think it's well known that you can compute or derive the what's it called, the first cohomology of that with that ambiguity group. So I'm not sure if you have looked into the cohomology group of Penrose tiling.
Yeah. So let me just share the picture for those of you who are not familiar with this. So this is the Penrose triangle, the tribar, I guess. This is what you're referring to, right?
Yeah, right.
Yeah, so this optical illusion, because this is an impossible object. You can't really have an object like this. Yeah, I don't think there's a connection between the tiling and this thing. Like Penrose, he did a lot of things, right? He's a really great mathematician. He did a lot of things in different areas. I don't think there's a connection between the Penrose tiling and the Penrose triangle. I'm not sure. Your second question about the cohomology group.
Yeah. Maybe of Penrose tiling.
Yeah, I'm not sure about that. Let's see. How would you I haven't thought about that at all, the topology of it.
Right.
But I guess one thing you could do is that you could maybe rewrite the Penrose tiling as a graph, right?
Mm-hmm.
And then you can think of the topology on that graph, something like that. That could be a way to study the cohomology.
Right.
Yeah. I don't know. I haven't heard of that. It's an interesting idea. I don't know anyone who's doing that, but I do know this Penrose tiling does appear in different branches of mathematics. Okay, because primarily I'm looking at it in terms of analysis. I work in mathematical physics, and that's where I'm mostly interested. But I'm sure there's something about that in topology as well, because you could do that, right? Like you could choose points in the Penrose tiling to be vertices in the graph. So you could have an infinite graph that takes that Penrose tiling structure, and of course you could ask about questions in topology like what's the cohomology group and things like that.
Yeah. Right.
So I haven't heard of any research on that area, but it seems like something you could do. I'm not sure it's something that has been done. Yeah, so maybe that's a good topic for a grad student or something to look at.
Okay.
Great question, Johnny. Appreciate it.
Thank you.
Okay.
All right. Any other questions? Actually, the topic by Dr. Darren is very interesting. Okay, for some of I think we have a group of students here as well. So those who are interested, also we can contact Dr. Darren, for more details about the how to work on this topic aperiodic. Yeah, very interesting.
Yeah.
All right.
So to contact me, you can go to my website, so www.ong.my. My contact information is there. Don't call my office phone number because I'm not in my office. The university is closed. But my email is there. You can contact me. Just go to my website.
Email.
Just
send an email.
Yeah. So my email is Darren Ong at xmu.edu.my. Happy to talk to you about any of this.
Yeah. Okay. Good. All right. So again, once again, the final time. Any questions? So I guess no. So then with that, I think thanks again, Dr. Darren. Yeah, it's a very interesting talk. Yeah. Okay. So nobody can clap. So this one, I don't know. Webex, we can have the clap hand, but his one, I don't know how to do the clap hand.
I don't think we have it.
Okay. Again, so thank you so much, Darren. Thank you. Thanks a lot for your time. Yeah.
Thank you, everyone.
I hope you can come again to give more talks in the future. And as you say, hopefully there's a time that you can come to visit here, or we can revisit the Xiamen University there. All right. Okay. So thank you so much. And then with that, we will end the seminar this morning. All right. Okay. So thank you so much. And I forgot to open my video. No wonder. Yeah. Sorry. Okay.
Okay. Bye, everyone.
Right. Bye, everyone. Okay. And stay safe.